After the achievement of the new realization of numbers via our isonumbers, our group essentially experienced one of the most exhilarating periods of our life. The reason is because as I said before, the entire mathematics of the 20th century, at least the mathematics used in physics, mathematics underlying Lie theory, is essentially based on fields. So once we lift the basic unit and we lift the field, then the totality of the mathematics underlying Lie theory must be generalized in a compatible way. If only one entity is missed in this lifting, then the theorem catastrophic inconsistency are activated in an unavoidable way. I urge colleagues to verify this point, because if they find any entity, anything, sinus, cosinus, any object, the notion of tangent line, any mathematical object whatsoever or definition whatsoever that can escape the need of a lifting, isotopic lifting, to achieve a consistent formulation of the Santilli Lie-isotopic theory, please bring it to my attention, because it will be a very important discovery. Very well. So we went into an incredible pace of activity of generalizing as much as we possibly could in an isotopic axiom-preserving way, as it was the case for the iso field, because we needed this formulation to apply hadronic mechanics to concrete problem. Vice versa, without the isotopy of the rest of the mathematics, we were completely unable to do any practical application and experimental verification of hadronic mechanics. Very well, so the first lifting, of course, was that of space, which I did in 1983 at Nuovo Cimento. And let's review very conceptually. We'll have a separate lecture, lecture 3A, on the isotopy of Poincaré, in which we will enter into this notion in a much more accurate way. But at this moment, let's remember that what is a metric or a pseudometric field is as what is well known, is defined on a field. In this case, let's assume a real field. And then it's characterized by a metric, for instance, the Minkowski metric. And then this characterization is completed by a set of coordinates that are whose value are elements of a field. And with this basic notion, then geometrically we construct the fundamental entity, which is the line element, from which all the symmetries and the geometry and originate, as it is well known throughout this entire 20th century. Well, an isospace, or it's called Santilli isospace, I will refer to the isospace in this lecture, is basically is centered is constructed around an isofield. And the metric called isometric is essentially given for certain, must be given for certain reason of consistency that I don't have time to indicate, but they are fully explained in the literature. The isometric must be given by the product of the original metric multiplied not by the iso unit, but multiplied by the isotopic element. So we are talking about a very serious structural generalization of the metric, that from, in case of Minkowski, from 1, 1, 1 minus 1, we end up the most general possible functional dependence on the wave function, derivative of the wave function, everything provided that element T is positive, definite. But then the construction is completed by iso-coordinate, necessarily iso-coordinates, namely coordinates multiplied by the iso unit, because their value cannot be element of the field. It will be totally inconsistent. We'll end up in a minestrone, and it's not kosher. No, they have to be element of the iso field. Therefore, the iso coordinates are ordinary coordinates multiplied by the iso unit. And then you look at the new line element. This is, ladies and gentlemen, is the most general, conceivable line element that human mind can imagine under certain limitation, because everything we do has limitation. In this case, we are talking about a symmetric metric. Isotopy are reversible over time. Here, this indeed will remain reversible over time from a geometric viewpoint. We have to go to the Lie-admissible branch of hadronic mechanics to break the symmetry and broaden our view, go higher in the mountain so that the vista is bigger and better. But we cannot jump at that level because it will be difficult to follow this lecture if we present them at the highest possible level, which incidentally will be the multi-value hypervalued theory will be incomprehensible. So let's do isotopy first, and then we remove step by step their limitation and go to the next step. But let's see the consequences already here, because this is non-trivial. First, we immediately see the emergence of a new symmetry. We see the emergence of a new symmetry. For the case that this is original space is Minkowski, and this is iso-Minkowski, we see a new space-time symmetry. Ladies and gentlemen, this is not trivial. Indeed, I use this new symmetry to propose my own grand unification of electroweak and gravitational interaction by embedding the interaction precisely in the gravitation precisely in this degree of freedom. What is the degree of freedom? Well, the degree of freedom is due to the fact that the line element has to be an isoscalar, must be an element of isofield. So at the end of the line element, you must multiply by the iso unit, because this is a number multiplied by the iso unit. Once you see this, you have here inside, you have the inverse of t. Here you have the inverse of I. Outside you have I. Then it's very easy to see that if you multiply the isotopic element by a number, and you multiply the iso unit by the inverse of that number, this thing remains absolutely identical. And so therefore you have a symmetry. And we will see, for instance, one of the consequences we will see in lecture 3a, the Poincaré symmetry is 11-dimensional and not 10-dimensional as believed throughout the entire 20th century. And we will give rigorous proof of this property, because this multiplication by the unit applies also to the Minkowski space. And so therefore this new symmetry of space-time originates at the Minkowski level. Iso-Minkowski is only a consequence. Finally, another thing I want to indicate to your attention already now is the power of unification, at least at the level of the line element, of the isospaces. Normally you talk about Minkowski space and then Riemannian space, non-desarguation space, and many other type of space. Well, if you have the same signature, plus, 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 minus, the iso-Minkowski space unify all infinitely possible space-time with the signature plus, 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 minus. And all line elements are here. They are right there. So the power of unification is there, and it is not trivial, ladies and gentlemen. Indeed, my grand unification of electroweak and gravitational interaction is centrally based on the prior unification of special and general relativity. Or if you want, the prior unification of Minkowski and Riemann. Because if you remain with the conventional formulation, I believe the grand unification is not consistent. I'm not sure whether I will have time to present a lecture on this grand unification. It is studied in all details in my volume Isodual Theory of Antimatter, because it requires not only consistent grand unification, not only requires unification of special and general relativity, but also requires antimatter. Put in a different way, unless in a grand unification I see a gravitational consistent treatment of antimatter, I'm not interested in even looking at. Because electroweak interaction have a beautiful definition of matter and antimatter, then you go to gravitation. And the gravitation, you lose any capability with Riemann to characterize antimatter. Neutral, for instance, neutral antimatter, as we said in lecture 1. Under those conditions, ladies and gentlemen, I'm sorry, I don't even read the paper. Very well, let's go next. Let's go to the functional or isofunctional analysis. As I said at the beginning, was essentially constructed by Aringazin and Kaidishvili. I also did some contribution to the iso exponent and so on, but they have been the most active. And what is an iso function? Well, first of all, is an entity whose value is an isoscalar. So therefore, is an object, an ordinary function, multiplied by the iso unit. But that's not enough. The variable of an iso function must be isoscalar. So therefore, the variable, for instance, the coordinate has to be an ordinary coordinate multiplied by the iso unit. Very well. I cannot enter in all more details because it's a field apart. It requires a specific study. I can tell you this, however, unless the Santilli Lie-isotopic theory is treated with isofunctional analysis, you can be sure that it is catastrophically inconsistent. If you use ordinary sinus, cosinus, ordinary exponent, ordinary logarithm, you will have catastrophic inconsistencies most insidiously because you will not necessarily see them. Only the expert will identify, but you will see them later, in a much later, therefore at a much more damaging level. I only want to remember here the iso exponent, that the iso logarithm and the others that unfortunately I don't have the time to review. However, the isospherical coordinates will be discussed in detail in lecture 3A, which are very, very crucial for the lifting of the Poincare symmetry as well as for scattering theory. The next obligatory isotopic lifting for the proper formulation of hadronic mechanics was evidently that of the theory of linear operator on a Hilbert space defined over a field of complex number. I did this job in 1982 with the late Professor Hyul-Chun Myung, who was a very close and dear friend of mine. Unfortunately, he died recently. We published together a number of papers. He was also very active, particularly in the Lie admissible branch of hadronic mechanics, and I will be quoting him much more often when we studied irreversible processes. I think this was one of the few papers that he wrote for the Lie-isotopic part. Incidentally, just for the record, in early January of next year, 2011, from January 4 to 9, we will have an international conference on Lie admissible formulations of irreversible processes, with attendance from colleagues from virtually all developed countries. And I want to be on record that by my request, this conference has been dedicated to the memory of Professor Myung, one of the founders of hadronic mechanics. Very well. What is the objective of this study? The objective is what I said from lecture 1, repeated in lecture 2. When I look at the sun, and I have a repulsion to use the theory of a linear operator on a Hilbert space for the representation of interior process in the sun. Ladies and gentlemen, they are too complicated. Of course, you can get chairs, you can get big prizes, you can do very good physics with the theory of linear operator. But for me, it has been insufficient since my graduate studies in physics at the University of Torino. So the objective is to lift the Hilbert spaces into a non-linear form. Non-linear means non-linear in the wave function, careful, the most general possible non-linearity. Also, and this made the job much more difficult, the lifting had to be axiom preserving for various reasons that we will discuss later. Also to be in line with the isotopy. Remember, we started from Lie isotopy, axiom preserving lifting of Lie algebra, and then we have axiom preserving lifting of numbers of spaces, and the Hilbert space had to be necessarily the same. Well, it was rewarding to see that the objective was achieved in full, indeed. Let's look at it. This is the essence of a conventional Hilbert space with the states, the inner product, expectation values, normalization, etc. How do we construct iso-Hilbert spaces? Well, we construct iso-Hilbert spaces by sandwich in between any associative product with no exception, sandwiching the isotopic element, and then multiplying the inner product in the outside by the iso unit, because the numerical value has to be an iso number. Otherwise, you have minestrone and you have inconsistencies. So it's very easy to construct. Here are the expression, and you can see at the abstract level, since the iso unit and the isotopic element are positive definite, at the abstract level there is no distinction whatsoever between Hilbert space and what been called Myung, Hilbert, Myung, Santilli isospaces. There is no distinction to such an extent that we use now the same number, we use this formulation with the understanding, however, that the product is isotopic. So some of the papers may be insidious. People may think that, may have delusions, they are wrong. In reality, if they don't know isomathematics, they're just out of whack. Okay, very well. Let's see what's the meat, what's the substance. Yes, the substance is substantive. Let's see what, here is the associative modular action of an iso-Hermitian operator on an isostate. Fine, this is isotopic product. But look how simple it is here on the left. It's so easy. And it's virtually identical to the other one. But look on the right-hand side, ladies and gentlemen. Write explicitly the isotopic element as an arbitrary functional dependence. Therefore, iso-Hilbert space indeed allow the most, this has been proven proved by mathematicians to be the most general conceivable nonlinear eigenvalue equations. But that's not enough. Look at the right-hand side. This was crucial. Remember, I am a physicist. I have to do numbers, and the numbers have to be verified with experiment. I repeat and repeat this all the time because it helped me to, as a guide to construct the theory that I needed to achieve those objectives. Look on the right-hand side. The first eigenvalue is an iso number. But the iso number then is an isotopic product multiplied by isoket. The isotopic product means that there is the isotopic element. So here you have iso unit and its inverse. So they cancel out. At the end you have an ordinary number. So hadronic mechanics produces ordinary number at the end of all the calculation because only ordinary numbers can actually be measured in a laboratory. And iso numbers are a mathematical abstraction. It was also intriguing to verify that the iso inner or the Hilbert space, the inner product has indeed the same new degree of freedom of metric spaces, under the sole condition that you multiply the inner product by ordinary unit of the field that you have assumed. If you only do that, then you can see in the interior, you can sandwich in the interior a constant, let's say k. Multiply the unit by the inverse of a k, and this is an invariance. This is essentially the same as what happened for the metric spaces. So, as a matter of fact, to such an extent that iso-Hilbert space can be introduced as a realization of this new degree of freedom that parallels 100% that in metric spaces that we have indicated before, and thus very intriguing theoretical, mathematical, and experimental and applied that we will see in later on. I cannot dwell more on this, but there is one point of the theory of isolinear operator on an iso-Hilbert space that has to be brought to your attention. I did this also with Professor Myung and Professor Nishioka from Japan, called this entity the Dirac-Myung-Santilli delta function. Well, remember, everything has to be lifted for consistency. If you have one entity that is not lifted isotopic, you have a minestrone and you have inconsistency. So, and this is a mandatory lifting. So here you know that the Dirac delta function is defined by an integral on an exponent. We have the iso exponent, so it was very easy in 1982. Professor Myung and myself to replace to do the isotopy, and you end up with this expression. This is essentially a way of rewriting in terms of the other one. But look below. Look below. This is, ladies and gentlemen, those pictures, and they are worth 10 books. The Dirac function is a distribution and has a singularity, as it is well known. That singularity is at the foundation of many problems of 20th century mathematics, including the infinities in the scattering theory that have been questionable since their conception. The Dirac-Muon-Santilli function, first of all, is no longer a distribution, but is an ordinary function and has no longer necessarily a singularity at the origin. Ladies and gentlemen, this is the foundation for a convergent scattering theory that we have already developed. I don't know whether we will present it in this lecture series. We hope so, but it has already been accepted for publication with many articles. It's a theory that essentially, with a very fast convergence, you can stop the approximation of the second, third term. It's already good, and there is no need whatsoever of removing the infinities. No need to removing the infinities. I worked on this point for years because I learned how to remove the infinities in a variety of ways. Therefore, this implies possibility of manipulating the removal of the infinities. Therefore, achieving the desired result rather than having an intrinsic numerical final value. Incidentally, Dirac during the last year, he proposed the construction of a new scattering theory, new field theory that avoids the divergences. Because of this, it was discredited. Paul Dirac was discredited by my colleagues. I was at Harvard at that time, and MIT. They discredited Dirac. He was isolated. He was in retirement in Florida. Well, not for me. Indeed, I spent a trip to visit Dirac. It was in 1982, I believe, soon after I discovered this, and I met him, and as you know, he was a magnificent person. He was very taciturn, and he looked at me very strangely. When I presented, I knew, however, of his dream of avoiding divergency, and I present this as well, the isocanonical series in which the convergence is evident. I remember he dilated his eye, and all of a sudden he lifted up and started walking walking up and down for 2 or 3 minutes. I was intimidated. I did not know what to say or what to do. After a while, he stopped and looked at me and said, "Dr. Santilli, please send me the paper. I'm interested in looking at them." Unfortunately, Professor Dirac died immediately thereafter. If he had been lived a few more years, I think the history of theoretical physics would have been changed dramatically because of his. He was indeed one of the biggest geniuses of the 20th century. Very well. Okay, let's go to the next. So, to complete all this lifting of everything we could possibly lift, that here we just summarized very briefly. Basically, we reconstructed linearity, locality, and unitarity on isospaces over isofield. What does it mean? It means, for instance, in an ordinary space, we have a highly nonlinear theory. Okay, we reformulate the theory, we identify an iso-unit in such a way that the nonlinear theory is represented identically, no transformation, identically is represented. But in such a way that it verifies the axiom of linearity on isospace. This is essentially a trivial occurrence because all the nonlinear terms, look at here, this is a highly nonlinear conventional quantum mechanical equation, violates the superposition principle. My opinion, I can never was able to use it in any composite system. It's just a mathematical exercise. But when you see you reformulate in this way, all the nonlinear terms are in the isotopic element, and the conventional interaction are in the Hamiltonian. Ladies and gentlemen, the right-hand side verifies all axioms of linearity in the right, in isospace over isofield. Same principle occurs for locality. Essentially, we embedded all non-local terms in the iso-unit. So the theory is everywhere local differential except at iso-unit. That's the principle of the new topology known as Ganfornina, as well as studied by late Professor Zagas and Sorlas. And finally, the unitarity. You see, you have any theory which is non-unitary on a conventional Hilbert space over a conventional field. There always exists an identical reformulation. This is the reformulation, identical. There is an infinite family of identical reformulation, but out of which you choose whatever is the best, the one that represents the non-self-adjoint forces. So it's an identical formulation under which the reformulated transformation verifies the axiom of unitarity on an iso-Hilbert space over an isofield. Think in a different way, ladies and gentlemen, unless with the isomathematic had reconstructed linearity, locality, and unitarity on isospaces over isofield, Santilli Lie-isotopic theory would have been inconsistent. In other words, do you remember, Lie theory is linear, local, and unitary. Now, we managed to broaden the theory, but the consistency of the theory is that because we reconstructed the original the original main feature on isospaces over isofield, and that was the reason for the primary reason for the achievement of consistency. Very well, here another major stumbling block in the history of the construction of hadronic mechanics and related formulations. After years of lifting isotopically everything that we could possibly identify from exponentiation, sinus and cosinus, and the most complicated functional analysis, integral geometry, symplectic geometry, various geometry were lifted. I don't have time to indicate it. Maybe we have a separate lecture on isogeometry. Anyhow, after all this effort, ladies and gentlemen, the hadronic mechanics had still not achieved invariance. And therefore, it was not a viable theory from a physical viewpoint. It was essentially a Polaroid. A Polaroid that would provide a Polaroid picture of interior dynamical problem, but as far as time evolution is concerned, in my opinion, had no value whatsoever. Okay, so this additional stumbling block, like the one for the numbers, this was much more serious, because at least for the iso number, I knew what I had to look at. I had to look at the axiom of the field. I simply did not have the courage, because of respect for the magnificent mathematicians who achieved the classification of numbers. So it was an emotional issue, but I know the target. I knew the target. Well, the problem here was much more serious. It was potentially devastating. It means the tens of years of research would have gone down the drain. Why? Why was more insidious? Because we did not know where the inconsistency was. We had lifted everything. Everything we could possibly lift isotopically, we had done it. Still, we did the verification, also to see the gravity of the situation is that at that time, we are talking about early 90s, at that time, despite all the efforts, we had been still unable to achieve a consistent representation of the linear momentum in hadronic mechanics. Lacking the linear momentum, I could not formulate the angular momentum, so the theory was structurally incomplete. And so therefore, we had to, it was a period of great depression because of disappointment, because simply we did not know where to look at, how and where to resolve this insufficiency. Finally, in 1995, we had one of our plenary international conference, this time at the Castle Prince Pignatelli in Molise, Italy, where we had this international conference on hadronic mechanics. It was attended by over 150 scientists from many different countries. At that moment, out of desperation, stimulated by this very exciting environment, it was a fantastic meeting because it was totally free. The speakers, very distinguished speakers from high-ranking institutions, were free to express their doubts and their wishes and desire and so on. So out of sheer desperation and excitement, I finally decided to inspect Newton and Leibniz differential calculus. It was the only one left. Everything else had been lifted. Once I had the courage, again, because of respect from Newton, by far everything I say starts from Newton. So my respect and devotion from Newton should not even be mentioned. So I did not have the courage to look at this differential calculus. But when I did look at the axiom of the differential calculus, again the solution was instantaneous and immediate. And the main result is that, ladies and gentlemen, despite what has been stated for centuries since Newton time, the differential calculus does indeed depend on the assumed basic unit. Because if that basic unit is indeed as a functional dependence on the variable of differentiation, then the differential calculus that we have studied in PhD school as well as undergraduate school, it is no longer applicable. And indeed it was very, very instantaneous to lift the differential calculus in an isotopic way. As you can see here, the variable has to be an isovariable. So you see the appearance of the iso unit as part of the differentiation process. So you cannot escape the iso unit, or the unit if you want. And then there is necessarily, for consistency condition, the multiplication to the left of the isotopic element. So basically you see here that if the iso unit does not depend explicitly or implicitly in the local variable, then isodifferential, the way it is called, and differential coincide. The I and T, they cancel because they are inverse of each other. However, again, if the iso unit has the local dependence on the variable, then the difference between differential and isodifferential is rather substantial indeed. This has very deep physical implication in all, visually, in many different application. The same, of course, for the partial derivative. Once you lift the differential, partial derivative has to be lifted. Once those two simple formula was achieved, everything, hadronic mechanics literally exploded. Studies on hadronic mechanics literally exploded in dozens and dozens of articles per year, and monographs and books, because we knew that the linear momentum could be realized via the isodifferential. That's why we did not have the isodifferential to formulate the linear momentum in a consistent way. So once we had the linear momentum properly formulated, angular momentum, and then immediately we went to application and to industrial application. Finally, we had reached the point in which we had reached sufficient maturity to indeed propose new clean energies and fuels, as we will see. In retrospect, let us remember that Newton had to invent, with Leibniz of course, the differential calculus as a necessary condition to formulate his famous equations. Without the differential calculus, Newton would have been a magnificent unknown. Nobody will ever remember him. Is the differential calculus that allowed. Here is the importance of first mathematics for the correct treatment of physical problem, and not enough. New mathematics. See the power of Newton. He developed a new mathematics to treat problems that his predecessor could not properly formulate. Newton is Newton because he followed that process. He had the courage to develop new mathematics, in this case, new differential calculus, and then is now part of history, justly so. Well, but I had to do the same. Ladies, I have no comparison, my God. I have no comparison with such a giant. However, the reality remains that until I lifted the Newton differential calculus, everything I did had no sense. It was inconsistency. Was inconsistent. Only after achieving the isotopy of Newton's calculus, then interesting things emerge. Look at here. Look at this. On the left-hand side, you have self-adjoint and non-self-adjoint forces. Remember, for lecture 2a, variational potential and non-potential forces. Look on the right-hand side. The non-self-adjoint forces disappear, even though there is an identity. So this Newton equation is identically reformulated. In this isotopic form on the right-hand side, the non-potential forces disappear. Where is it gone? This is an identical reformulation. It's gone in the iso unit. That's precisely a representation of non-self-adjoint interaction with the iso-unit, in this case with the differential calculus, iso-differential calculus. Ladies and gentlemen, meditate a moment on this identical reformulation. The implications are very substantial. First of all, this is now variationally self-adjoint. This admits a first-order action principle. Therefore, just to throw one example, for instance, this isotopic reformulation allows, for the first time to my knowledge, to apply the optimal control theory to the shape of the wing of a plane, inclusive of all possible resistance, including into the differential form of the resistance. I repeat, the wing of a plane cannot be subjected to an optimal control theory because of the lack of an action principle. Without the action principle, there is no optimal control theory. But since, thanks to the embedding, thanks to the new the differential calculus and the embedding of non-potential interaction in the differential, the first order action is possible. And then, therefore, once you have a first order, with all four possible resistive forces that you want, and when you see the topology, and you see that indeed you can have the actual shape of the wing, it's no longer point. Here you have points. Here you have actually extended deformable shape. Okay, so the jump from here to the right is substantial, ladies and gentlemen. It's not trivial, as we will see hopefully in details in the next section. But but apart from that, once you have you see this from here, you can already conclude that hadronic mechanics achieved for the first time in my knowledge a consistent operator form of non-potential interaction. Remember, non-potential interaction where it has been impossible to express them in an operator form throughout the entire 20th century. And one of the reasons is that you don't have an action principle. Since you don't have an action principle, you don't have quantization. You have a very nice formulation for point particle with Newton, but you don't have an operator. You cannot even formulate an operator counterpart. This allows an operator counterpart. Conclusion, this allows the formulation of the study of interior dynamical problem from A to Z, from Newton all the way to second quantization. So this very simple formula, ladies and gentlemen, are by far non-trivial. Just the industrial application that I hope to indicate that are significant. Very well, let me close with, so finally, hadronic mechanics reached consistency. Finally, after so many years, so many ups and downs in enthusiasm, and then followed by depression. But finally, we have been so determined because the study was worth it. Finally, it was achieved. I have a few final charts because I believe are necessary as a complement of this lecture. First of all, there is a very easy way of constructing isomathematics. I presented particularly for theoretical physicists. For mathematicians, there is no need to, because as I indicated, they use the formula of the conventional mathematics and just subject the formula to a broader interpretation. That's all, but the formula are the same. But for a physicist, it is different. Well, it's very easy to construct isomathematics by using non-unitary transformation applied careful to the totality of the formulation of quantum mechanics, with no exception. You miss one, and you end up with a minestrone, and you have inconsistency. So you begin with the unit. Conventional unit of quantum, that's Planck's constant. Planck's constant is lifted into an integral differential operator. We will see why. And that's the iso unit. The numbers are lifted into iso number. And similarly, you can see all the other expression. Hilbert space also very easily lifted with a non-unitary transform into iso-Hilbert space. The conventional eigenvalue expression of quantum mechanics is very easily lifted by a non-unitary transform into the fundamental iso-eigenvalue equation of hadronic mechanics. Notice also the very natural emergence of the sandwiching of the isotopic element in between the Hamiltonian and the isostate. What is also very intriguing is to see that Santilli Lie-isotopic theory can indeed be obtained via non-unitary transform of the conventional Lie theory. But there is a trap. There is a trap, especially for both mathematicians and theoreticians who are eager to reach conclusion of non-triviality. Oh, I've seen many people when they see this thing, oh, Dr. Santilli, this is trivial, there's no novelty. It is because this type of judgment, especially when they are thrown without prior technical knowledge, usually are self-damaging. That's all. You see, this non-unitary transform applies only for what we call the regular formulation of Santilli Lie-isotopic theory, namely the formulation with constant, with the structural constant given by constant. If you remember from the preceding lecture 2a, we have a second class of formulation, much less trivial, in which we have structure function, which is the one that at least I am personally much more interested, because that's where the novelty of the physics is. Ladies and gentlemen, that formulation of the Santilli Lie-isotopic theory with structure function, I can assure you, you cannot reach it with a unitary transform. No, it is a structural novelty indeed. Even to the axiom remain still Lie's axiom. Very well, another point that is very important is to see that isomathematics and therefore hadronic mechanics is not invariant under a non-unitary transform formulated on a Hilbert space over a field. Seems an inconsistency, because here I have a non-unitary theory. I subject the non-unitary theory to another non-unitary transformation. Why I don't have invariance? No, you don't have invariance. It is very important to see the very root of what happens. It's very important to understand the essence of this series of lectures. Here is start with the non-unitary transform. Then you have the associative product. Okay, then you lift the associative product to you map the associative under the non-unitary transform left and right, and you do the calculation. You still and assure the end result is still iso-associative. You have not violated the axiom of associativity. Of course not. A non-unitary transform applied to an associative product cannot change the associativity of the product. This was expected. But, look at the isotopic element. The isotopic element has become a monster after a non-unitary transform. What does this mean? This is not pure mathematics, ladies and gentlemen. This means that you have changed the system that you have represented. In other words, suppose you were representing originally a spaceship during re-entry in atmosphere. After a non-unitary transform, you may be representing an electron in the core of a star. You jump from horses to apple or something like that. You have changed the system. So that's why a necessary condition for the invariance, true invariance of hadronic mechanics, is that iso unit has to be invariant, cannot be changed. This iso unit is trivially non-invariant under non-unitary transformation, as it is the isotopic element. So this is my final chart of this lecture. Essentially indicates that indeed we do have invariance of the iso unit. Oh yes, indeed. This is the central point that I left at the very end of this lecture, in purpose, of course. And but you cannot treat the invariance of an isotopic theory with the mathematics of a conventional theory. This is usually the usual minestrone I mentioned many times. You end up with inconsistency. No. The invariance has to be studied within the context of isomathematics. Then you can correctly formulate it and resolve it one way or the other. But you cannot study the invariance of one theory by using the mathematics of another. It makes no mathematics or physical sense. So what does this mean? This means that you start with a non-unitary transform. Yes, fine. But you have to reformulate it into an iso-unitary form. You have to factor out the isotopic element, the square root of the isotopic element. When you do that, this non-unitary transform on a conventional Hilbert space becomes a fully unitary transform on the iso-Hilbert space. Once you investigate the invariance of isomathematics under an iso-unitary transform, you immediately see that the iso-unit is invariant, numerically invariant, and the product is numerically not altered at all. The isounity stayed numerically the same. And the product itself, the isotopic elements, stay numerically the same. This means that you have preserved the original system, namely you have preserved the non-self-adjoint interaction in an invariant way. And this was the central objective of isomathematics that was indeed finally achieved in full. And that is why it is my opinion and the opinion of many colleagues that hadronic mechanics and this underlying mathematics, indeed, they do have a realistic chance of withstanding the test of time. Okay, well, I would like to close this lecture with a cute episode, a real episode that happened. This is the Castle Pignatelli in Monteroduni, where we had the 1995 plenary conference of all researchers from all over the world working on hadronic mechanics. The true episode is the following. We had, one day we had a very important session from a biologist, actually a member from Nobel Committee, so it was a very, I cannot mention names, but it was discussing about the need of surpassing quantum mechanics in biology, a very, very intriguing and an important topic in my view. All of a sudden, there were, outside the castle, there were horrendous yellings, unbelievable yelling, so loud, of so many people yelling, so loud that the session had to be stopped. So I rushed to the window to see what was going on. And what was going on was that simply there was a bunch of Italians playing cards, Italian style. And the Italian style of playing cards is yelling at the loudest possible way, disagreeing, but always without names, in a very respectful way. But that's the Italian style. So I went inside and I told the participant that the Italians are playing cards, that's what they are yelling. So everybody went to the top of the castle and looked at the scene, and it was very funny, and it was cute. Then of course we told the Italians, go somewhere else. They did, very respect. They didn't know that there was, we had a scientific meeting inside, and the session resumed, and it was concluded very, very happily. I thought this really episode on the construction of hadronic mechanics will may be of interest to some of you. Thank you for the attention.
Professor Santilli, I am shocked to discover that there exist infinitely many series of prime numbers. Can you elaborate on this?
Well, dear colleague, you are not alone in being shocked. Indeed, I have seen mathematicians in number theory to be equally shocked, as I indicated before during the lecture, because they have recognized that some of their statements in papers published in top referee mathematics journals were incomplete, and because, as I indicated earlier, the correct formulation of any statement in number theory requires first the identification of the basic number and then the statement of what follows. And so there are indeed infinitely many series of different prime numbers that have yet to be studied. It's a completely untapped territory. Thanks for the question.
Professor Santilli, I do not understand your isotopic unification of metric spaces and geometries. The Riemannian and Fenslerian geometries are mathematically different and cannot be unified in a view. How can you convince me to the contrary?
That is also an excellent question, and I appreciated that you posed that question because it's a debatable issue. Namely, what is the meaning of a isotopic unification of geometry that conventionally are known to be very different in structure, such as, for instance, Minkowski and Riemannian geometry are known to be very different. What is the meaning of their isotopic unification? It is a debatable formulation, because in reality what we have a new geometry, in this case the iso-Minkowski geometry, that admits not only the Minkowskian line element but also the Riemannian line element. So in this case it is a kind of unified formulation, but we are talking about a basically new geometry, however. I use the word unification because that's what they've been doing in unifying special and general relativity as a necessity to achieve grand unification and for other purposes. So the unification from our viewpoint is necessary, but, but from a mathematical viewpoint, different formulations are equally acceptable.
Professor Santilli, I'm very interested in the Dirac-Myung-Santilli isodelta distribution. What are its implications?
Thank you for this question, very pertinent. You have put the finger on the very heart of hadronic mathematics and mechanics. As you know, the Dirac-delta distribution is at the center of quantum mechanics and quantum field theory. Therefore, you have to expect that the Dirac-Myung-Santilli isodelta function is no longer a distribution, is indeed at the very heart of, of this series of lectures. The implications are very intriguing indeed. You will see that there is the birth of a brand new scattering theory without divergences, so there is no need of manipulation with the techniques, so-called techniques, to remove the infinities from an infinity. When you have an infinity, you remove the infinity, the number comes out. Ladies and gentlemen, with all due respect, I cannot accept it as a final. If it is presented as a plausible result, I will respect it and accept it as science. If it is instead presented after removing infinity from the infinity, presented as a final scientific result, I'm sorry, I disagree dramatically, because that is not science, it becomes politics. Very well, but in addition to that, besides the removal of the infinities, you see, I made a claim in a strong position, I assume a strong position in lecture 1A, that the special relativity is exactly valid in a particle accelerator. Yes, it is, tested everywhere, but it's a dramatically different situation when a proton at high energy leaves the accelerator and hits the nucleus. At that moment, we have dramatic events, structural irreversibility, all the most general possible interaction, nonlinear, non-local, and non-potential interaction. The conventional so-called experimental results are based on the 20th century theory, which is linear, local, and potential. Ladies and gentlemen, as we will see, there is a realistic possibility that a number of so-called experimental results may eventually emerge as being only experimental beliefs of the time. We will see whether this is correct or false. Thank you for your assistance.